Hello, everyone. This is again Professor Barish, and this video is for my Camden County College students. This is the first video of 4 videos that I'll be doing for Chapter 7, which is what's called hypothesis tests. The last 2 weeks, we were discussing Chapter 6, confidence intervals. Confidence intervals were intervals that were used to estimate a population mean or a population proportion. Suppose a researcher wanted to do some research and has an estimated guess of what a population parameter could be. And let's say he or she wanted to run a sample and get some data to see if that conjecture or hypothesis has any validity to it. That's what we call a hypothesis test. And that's what we're going to discuss this week and next week, is Chapter 7. There are 4 sections, there's actually 5 sections in Chapter 7. Section 7.5 we will not cover in this course. So we're only going to cover sections 1, 2, 3, and 4 of Chapter 7. So today we're going to cover section 1 of Chapter 7, which is really an introduction to what a hypothesis test is, and some of the terminology and some of the ideas that are behind it. And this is really the basis of why we have modern statistics. Modern statistics is there to support people who do research, people who want to know, want to find some evidence, maybe if a particular drug works or not, like a drug for treating the coronavirus, or maybe a reading program in a school to see if it's working or not, that sort of thing. And they may have some idea of the current state of affairs. There might be a hypothesis about what is currently going on. Let's say in a school, the school is currently using an old reading program. They're not satisfied with the results, so they're going to try a new reading program, and they're going to compare, okay, see if there's an improvement with the new reading program. Those are the types of things that researchers are interested in, and statistics is a way of doing this by doing some sort of hypothesis test. All right, so what we're going to do is go right to the textbook in 7.1. If you have your textbook along, you can follow along. All right, and let's go ahead and do that. Let's see if I can, there we go. All right, so this is 7.1, hypothesis test. All right, so there's a definition almost immediately in the textbook about what a hypothesis test is. It says it's a process that uses sample statistics to test a claim about the value of a population parameter. So again, someone is making a claim about a population parameter. They're not just estimating it in this case, we're actually coming up with a claim about it, some numeric claim. And then we're going to test it using the sample statistics. So since we're going to use sample statistics, once again, we're going to use the sample distributions. The sample distribution of population means, if we're testing a population mean, or sample statistics for a population or population proportion, if we have a question about a proportion. So we're going to be using the mean and the standard error, all right, for sampling distribution like we did in Chapter 6. All right. Once again, this here is a picture of a normal curve that's used for a sampling distribution of sample means, right? And that's what this curve is here. And the mean of the sampling distribution equals the mean of the population, which happens to be 50 in this case here. And so they have 50 here as the sampling distribution and population mean. And then they just pick a mean for a particular sample. A sample which has a mean of 47. And so that is the dot that's represented here. Okay. So typically, in many cases, there's a difference between the sample mean and the mean of the population. So what we're going to, anytime we do research and we make a claim about a population mean or a proportion, we're going to call that the hypothesized mean if it's a mean, or a hypothesized proportion if it's a proportion. But it's strictly dealing with the population mean and population proportion. All right, and then we're going to use the sample data to do a test. All right, and that's the whole idea here. We're going to be doing testing using the sample data, but the hypothesis is about the population parameter, either the population mean or the population proportion. Okay. So anytime we do a hypothesis test, we're going to have two hypotheses that are going to be competing against one another. The first hypothesis is called the null hypothesis. It has an H with a little 0 next to it. Typically, we call it H sub 0, or null hypothesis. Now, and then we have the competing hypothesis, which is called the alternative hypothesis, H sub A meaning alternative. All right. Now, it mentions in this definition here about the signs that we're going to use, the operations that we're going to use for each of the hypotheses. For example, it says the null hypothesis, we have a statement. It's going to be a symbolic statement, not in words, but in symbols. And we're going to have either less than or equal to, or greater than or equal to in the symbolic statement for the null hypothesis. So notice there's an equal in all three of these. This one is just a plain old equal. This is a less than or equal to, and this is a greater than or equal to. So the null hypothesis always has one of these three. The alternative hypothesis never has these three. It always has these three: greater than, not equal to, or less than. All right? All right. Now, there are three sets of hypotheses. Here's one set here. If the null hypothesis is mu, and they're using mu here, but we could use p if it's a proportion. But this is the population mean. If the population mean mu is less than or equal to some number k, if that is the null hypothesis, in other words, it's let's see, the first case here of the null hypothesis, then the alternative has to be greater than. Now, in the textbook here, they made a mistake here. It should just say k here. There shouldn't be apostrophe there. When you do a hypothesis test, the null and alternative hypothesis, this is one of the rules, is that this number here, these numbers here have to match. This k and this k with an apostrophe there, they have to be the same number. So they shouldn't have put an apostrophe there. They should have said k. But both of these numbers have to match. They have to be the same number. Now the question is, if the null is less than or equal to, why is the alternative greater than? Well, the reason is because the greater than is the complement of less than or equal to, right? If you say the height is less than or equal to 7, then the complement of it would be greater than 7 to include all possible numbers. Okay, so less than or equal to is the null, greater than must be the alternative. Likewise, if the null hypothesis has greater than or equal to, that's the this one right here, u or p, depending on the situation, greater than or equal to k, the complement of that must be less than. Mu is less than k. And finally, if the null hypothesis is equal to a number, then the alternative must be not equal to. Now, a null and alternative hypothesis must have the three components. It must have the population parameter. It must have for the null hypothesis, must have one of these three symbols, and it must have a number after it. And the alternative must have the same symbol, the population parameter symbol. It must have the complement of the first symbol, and these two numbers must match. Okay, now, here's some verbal statements where they give you some words and you've translated into symbols. For example, if the null hypothesis is saying greater than or equal to, well, that's this symbol. I hope you know that. Sometimes people get confused with this phrase here, at least. At least means greater than or equal to. It means the same thing here. This is a little more complicated. Not less than means greater than or equal to. Not shorter than K also means greater than or equal to. Now for the alternative here, less than, below, fewer than, shorter than, I think all of those hopefully make sense to you. For the null hypothesis, which has less than or equal to, well, that's less than or equal to. That's one phrase you can use. At most also means less than or equal to. Not more than also means less than or equal to. And not longer than means less than or equal to. And then the alternative over here, it's greater than, above, more than, longer than. That makes sense. And I think these hopefully make sense to you here. There shouldn't be any confusion. The equal sign should be equal to. It could just say, give the number itself without saying equal to or greater than or less than, and you know that means equal to. They put the word exactly there, the same as, not change from, all of those mean equal to. And then we have these phrases here, which all means not equal to. So this is a very useful chart. And if you do have maybe some confusion sometime about these phrases, and you're doing homework or you're doing a test, it would be good to have a copy of this chart right in front of you so that you could just simply look it up in the chart and determine what symbol that you should be using. All right, so that's a good chart here to be used, and it's nice to have this. Other textbooks that I've seen in introductory statistics does not have this sort of chart, so this is a nice little chart, little benefit of using this textbook. All right, stating the null and alternative hypotheses. So you should be able to take a word problem, a word statement, and translate it into the null and alternative hypothesis. Now, in typical problems, they'll just give you one of the hypotheses. They will describe it as a claim. It could be either the null or alternative hypothesis. And then you're supposed to figure out what the competing hypothesis is also by finding the complement of it. Let's do an example. Number one here, it says a school publicizes that the proportion of its students who are involved in at least one extracurricular activity is 61%. The word is here indicates equal to. And where are the equal to signs? Well, they go into the null hypothesis, correct? Equal to, less than or equal to, greater than or equal to, always in the null hypothesis. So you can see here, since it's a proportion problem, we use the population parameter P equal to 0.61, and that is the claim. So the alternative would be the complement of equal to, which is not equal to 0.61. P is not equal to 6.1, and these are the null and alternative hypotheses, where the null hypothesis is the claim. Okay. Number two, a car dealership announces that the mean time for an oil change is less than 15 minutes. Now, less than is not one of the choices for the null hypothesis, therefore it must be the alternative hypothesis. So in this case, the claim is the alternative hypothesis, less than. It is a mean problem because it is measuring, it's giving time here, which is something that we measure. And so the alternative hypothesis, which is the claim, is mu is less than 15 minutes, which means the null hypothesis must be the complement of it. Mu is greater than or equal to 15 minutes. And finally, the last one says a company advertises that the mean life of its furnaces is more than 18 years. Well, more than is also is not one of the choices for the null hypothesis, it's one of the choices for the alternative hypothesis. So in this case, again, it's something that we measure, so it's going to be the mean. And so we're going to say mu is greater than 18 is the alternative hypothesis, it's the claim. And therefore the null, which is the complement of it, must be mu is less than or equal to 18 years. All right, that's it. All right, and then give you some more examples here. All right, just see something here. I guess that's it. Now, one of the things you should remember also is that when we do a hypothesis test, it's always about the population parameter. It's never about the sample statistic. In other words, we'll never see X bar here. X bar should never be in the alternative null or alternative hypothesis. And in the same way, for a proportion problem, we would never see the sample proportion p hat here or here. It's always the population parameter that's being tested, not the sample statistic. Now, when we do a test, we're going to come up with one of two decisions. All right? Typically, the null hypothesis is the hypothesis that may have something to do with a current reality, current situation. And the alternative hypothesis is what the researcher is trying to determine. So there are two types of decisions that we will make when we do a hypothesis test. We have the two competing hypotheses, the null and alternative hypothesis. We're either going to reject the null hypothesis. In other words, there'll be enough statistical evidence, and I'll show you what that means a little bit later. There's enough statistical evidence to indicate that the null hypothesis, hypothesized value, or how the null hypothesis itself is not correct. All right, there's evidence that it's not correct, and that the alternative hypothesis we should go with. Or there's not enough evidence to reject the null hypothesis. Now, when we say there's not enough evidence to reject the null hypothesis, what we mean is that just that. It doesn't mean that we accept the null hypothesis as the truth. Let me give you an example. In a criminal court, I don't know if any of you have been a juror in a criminal trial, but if you have, you probably know that when the person comes into the room, the person who is being charged with a crime, the judge gives the jury some instructions and says, you need to treat that person as innocent, and then listen to the evidence by the prosecution and see if there's enough evidence to what they call go beyond a reasonable doubt. In other words, it's sufficient evidence so that you now move from innocence to guilt. In other words, you're going to reject the hypothesis that the person is innocent and then say there's sufficient evidence to indicate that the person is guilty, the alternative hypothesis. So the null hypothesis, what's accepted up front, is that the person is innocent. The alternative hypothesis is the person is guilty. So there's two possible results. One result is the person is guilty. The other result is what they say, not guilty. But what it really means, I'll put quotes around not guilty. It means there's not sufficient evidence to charge that person with a crime. It doesn't mean that the person didn't commit the crime. That has to be really clear. All right. So in hypothesis tests, when we use sample data, we don't really know the reality of the population parameter. We're guessing, we're hypothesizing about it. We're just seeing with the sample data if there's any evidence, either enough evidence to reject the null hypothesized value, or there's not enough evidence to reject it. That's really the two decisions that have to be made. All right. Now, since we have these two decisions to make, we don't really have full evidence of rejecting the null hypothesis or not rejecting it. We don't know reality in full. you may know it, maybe know it partly, then it's possible that when we come to our conclusion, either reject the null hypothesis or fail to reject it, that we made an error. Just like in a criminal trial. There's been plenty of cases, haven't there, where somebody's been jailed, right? Has been found guilty of a crime, maybe of murder, rape, whatever. And then years later, they found evidence that the person did not really commit the crime. All right, and they overturned it, and the person was released. So that's an error. Somebody made an error. That's a bad error for the person who had to be in jail for something they didn't do. The other type of error would be in the case where the jury found not enough evidence to convict the person, and yet the person committed the crime. So those are two types of errors. And in statistics, they actually classify these two types of errors. And they come up with this table to represent it. The first type of error was the one where if the person has been found guilty but was not really guilty. In other words, they rejected the null hypothesized assumption of innocence, and yet the person was really innocent. So if we reject the null hypothesis when it's actually true, this is called a type 1 error. A type 2 error would be the case where in the innocence guilt thing, where they did not find the person guilty, and yet the person really was guilty. So that's the case, what's called a type 2 error, when the null hypothesis is not rejected when it should have been, when it's actually false. So here's a table which shows the 4 possible outcomes of hypothesis test. The decision is based on statistics. We'll show you, I'll show you how that's done. And so here are the 2 decisions based on a sample, statistics, right? Incomplete information. And either we're going to do not reject the null or we're going to reject the null. And then up here is the truth of the null hypothesis, something that we really don't know in reality. Otherwise, if we knew it, why bother doing a test? So, but we're going to claim that either the null hypothesis is true in reality or it's false in reality. So there are 2 types of errors. And actually, when we do the test, we don't know necessarily if we committed an error or not. But again, we have to show that there are these 2 types of errors. Now, for example, if we decide to reject the null hypothesis, and let's say so we reject the null hypothesis, and let's say the null hypothesis is actually false. Well, then we made the right decision, haven't we? It's the correct decision. If we reject the null hypothesis and yet the null hypothesis is true, well, that's what this statement says up here. That's our that's a type 1 error. That's the type 1 error here. We reject the null, and yet the null is actually true. There's an error made. That's the type 1 error. On the other hand, if we do not reject the null hypothesis, if that's our decision, and the null hypothesis is actually true, then we made the correct decision, right? But if we did not reject the null and the null is actually false, that's the type 2 error here. Okay. All right. So those are the 2 types of errors. So out of these 4 types of decisions, 2 of them are correct, 2 of them are errors, and these are the definitions of the errors. Once again, our decision's either going to be reject the null or do not reject the null. If we reject the null and the null is true, actually, in reality, we've made a type 1 error. If we do not reject the null, and yet the null hypothesis is false, we've made a type 2 error. Now, there are, and this is, I think, on the next page here, and this is the example here with the criminal trial. Okay. Actually, let's do a couple examples here, and then we'll talk about the probabilities of type 1 and type 2 errors. All right. So this is all about identifying type 1 and type 2 errors if we're given a word problem, research problem. So here, the USDA Maybe you're familiar with the USDA. It's the United States Department of Agriculture, one of the largest agencies out of all the federal agencies. Anyway, they do deal with food safety, and suppose they have a limit for salmonella contamination for ground beef. You think the limit should be 0, right? But that's not possible. They would have to test every piece of meat, and nobody does that. So they test a sample of it, and if they're doing their job, the limit of salmonella poisoning in ground beef should be 7.5%. In other words, out of all the beef that's examined, 7.5% of it could have salmonella. That means 92.5% would not. So that's a limit there. A meat inspector reports that the ground beef produced by a company exceeds the USDA limit. All right. So a meat inspector comes in, does some sort of tests, and thinks that this company is above this limit here. So you perform a hypothesis test to determine whether the meat inspector's claim is true. When will a type 1 or type 2 error occur, and which error is more serious? Well, in this case here, this is a percent. So you're counting the number of pieces of meat that are examined. And so they say exceeds here. The meat inspector's claiming that the company exceeds this limit of 7.5%. So that when you say exceeds, that means greater than. That means the claim by the inspector is the alternative hypothesis. Since it's a proportion, its P is greater than 0.075. So we always write the proportion as a decimal, not as a percentage. So if this is the claim, then the null hypothesis is less than or equal to 0.075. P is less than or equal to 0.075. So what would be the null hypothesis here? Well, since the alternative hypothesis is the claim, all right, I'm sorry, I think I said what is the null hypothesis? What is the type 1 error? That's what I meant to say. So what's the type 1 error? Type 1 error is when we reject the null hypothesis and we go with the alternative hypothesis, when in actuality the null hypothesis is true. So in this particular case, we would have enough, the inspector would have enough evidence to reject the null. And what that would mean is there's just enough evidence to support the claim of this inspector that this company, the company's ground beef exceeds the 7.5% limit for salmonella. Okay. Now the type 1 error would say the inspector's claiming this, but in actuality, the null hypothesis is true. In actuality, the company is not exceeding that limit. Now, what would be the consequence of that? So the inspector is saying the company is in violation of this limit. Well, in actuality, it is not in violation. So the inspector will basically report that this company is exceeding it. Maybe the company has to stop producing the beef for some period of time. So this hurts the bottom line of the company. Is it okay for the consumer? Well, we just got rid of a good source of meat, but no harm, no foul for the consumer. Now the type 2 error would be where we do not reject the null when we should have rejected the null, and the null is false. So in this case, we don't reject this. In other words, the inspector says there's not enough evidence that the company is, there's not enough evidence to conclude that the company is exceeding the limit, when indeed the company is exceeding the limit. And the alternative hypothesis is true. Okay. What's the consequence of that? Well, if this test says the company is okay, it's not exceeding the limit, that means there's not going to be any restrictions on it, when in reality, it is exceeding the limit. And that means bad salmonella type meat is going out to the consumers. So that's bad. And I think the type 2 error here is worse than the type 1 error. So that's really the results of this. And it's written up here at the bottom. You can read through it. Okay. So that's type 1 and type 2 errors. Now, many times what researchers want to do before they actually do the research, see what happens in real research is there's the null hypothesis is really the common situation now, the common understanding, whatever. And then the research comes in and says, I have a competing theory. And so the researcher typically, not all the time, but typically is interested in rejecting that null hypothesis. That's really what they're doing the research for. They really want to reject the null hypothesis because then it would support their own theory. So they're very much interested in that type 1 error, because if they do reject the null hypothesis, there's a chance that the null hypothesis is actually true, and that their competing theory is false. So that is the probability of that happening is the probability of a type 1 error. So that's the error that typically researchers are interested in. And they want to set some limit to that up front before they actually do the research. So they want to determine up front what's called the probability of a type 1 error. Another term for that, by the way, is the level of significance. So the probability of a type 1 error is called the level of significance, and it's denoted by the Greek letter alpha. This letter here, alpha. The probability of a type 2 error is called beta. Now, you just need to know the definition of the probability of a type 2 error. Okay. And also, in a case where you have a problem, let's say you're doing homework or you're doing a test, and you've done your testing, again, you'll know how to do that later, and you come to the conclusion that there's not enough evidence to reject the null hypothesis. Now, what type of error would you make in that case? Well, that would be a type 2 error, possibly, right? That's the type of error you could make if you do not reject the null hypothesis, when the null hypothesis is actually false. That's the type 2 error. So that's the only other time where you maybe have to know what a type 2 error is, or beta, or probability of a type 2 error. Type 1 error would occur possibly if you end up rejecting the null hypothesis in your research. There's always that possibility that a null hypothesis is true. So that's the one that researchers typically focus on, is the alpha. And the beta, they don't focus so much on it. They could if they wanted to, but they don't. So when we do a research study, typically before the sample's actually drawn, or before the research is done, the researcher typically will come up with a limit to the type 1 error. In other words, for example, if they set the limit to 0.05, what they're basically saying, that's the maximum amount of possible error if they do reject the null hypothesis. Maximum amount of type 1 error that they want to have, all right, 5%, all right, a 5% chance that they made an error. Most people would say, okay, that's good enough. They could pick a 1%, like this one here, alpha is 0.01, but there are reasons why you may not want to get that small. You might think, let's make it as small as possible, type 1 error. Well, what ends up happening is the type 2 error ends up going up. So typically we want to balance between the type 1 and type 2 errors. And so most researchers typically pick 0.05. 0.10 would be a larger type 1 error that we're okay with, which is a 10% error. But these are the levels of significance, and they're chosen up front. And typically in a word problem, they will be given to you. All right, so you don't have to worry about the actual values here. They'll be given to you in the test. All right, so we have this maximum probability of a type 1 error that are willing to accept. And so what do? We do what's called a statistical test. We're going to calculate what's called a test statistic. And how we're going to do that, we're going to use formulas that we've seen before. All right. We're going to come up with Z statistics. We're going to come up with T statistics. And then we're going to find the probability of getting those statistics or something more extreme than those statistics. I'll show you how to do that. That's called a p-value. See the term p-value here. And then what the final step would be is to compare that p-value to the alpha that we chose. And again, I'll show you what I mean in a few minutes. Now, the only population parameters that we're going to test in Chapter 7 is the population mean and the population proportion. We will not be testing the variance, sigma squared. That's section 7.5, and that, in my view, is beyond the level of this course. It introduces a lot of additional information and complications that I think beginning students don't need at this point. So basically, we leave that out, and we just deal with the two types of hypothesis tests, one for a mean and one for a proportion. Okay. Now, here's another definition. This is the p-value or probability value that I mentioned a minute ago. So we always assume up front, just like in a criminal trial, we always assume up front that the person on trial is innocent until proven guilty. We're going to assume that the null hypothesis is true until we come up with enough evidence to think that it's not. So if we assume up front that the null hypothesis is true, then a p-value of a hypothesis test is the probability of obtaining a sample statistic with a value as extreme or more extreme than the one determined from the sample data. Okay, so again, I'll show you what that means in a couple minutes. So the test statistic, we're going to create a test statistic from the sample mean if we have a hypothesis about a population mean, or we're going to create a test statistic from a sample proportion if we are going to be if we have a hypothesis about a population proportion. Again, this third line here, we're not going to deal with. The test statistic itself that we're going to use, what's called a standardized test statistic. For a mean, we're going to use either a Z or a T. In other words, a standard normal or a T distribution. And for a proportion, we're going to use the Z only. This sounds similar, I hope, to what we did with confidence intervals. Remember, with confidence intervals, for a proportion, we use a Z critical value. And when we did an estimate of a population mean, we had two possibilities, a Z critical value and a T critical value. All right, and we'll be reviewing the same sort of thing here when we get to it. All right, so we're going to be using this, calculating this p-value thing. We're going to be comparing it to the alpha, and then we're going to make a decision whether to reject or not reject the null hypothesis. That's really the essence of this whole thing. Now, in hypothesis testing, there are three types of tests. No matter what population parameter we are testing, whether it's a mean or proportion, we're going to have three possible types of tests. So this is another chart that would be helpful to probably print, have next to you when you do your homework or take a test. So when we get to the next section 7.2, we're going to actually use these charts and so forth. So it'll be clear to you, hopefully, at that point. But for now, let's just go through it, and it'll become hopefully more clear to you next time when we speak. Now, when we do a test, we're going to use the alternative hypothesis to determine which of these three tests we're going to use. What are these three tests? The first one's called a left tail test. And that's when the alternative hypothesis has less than in it. So we ignore the null hypothesis. This is not involved with the testing. We simply look at the alternative hypothesis and look at the symbol here. If the symbol says less than, notice it's pointing to the left. That's a less than symbol. That means what we're going to do is we're going to calculate our test statistic. We're going to plot it on either a Z or T curve. Again, we'll see when we're going to use the Z and T later. And the 0 is always going to be in the middle, all right, because it's going to be a standardized Z, standard normal Z, or it's going to be a T. So mean is always going to be 0. So if our test statistic, if our alternative hypothesis is less than, we're going to plot or calculate that test statistic. We're going to plot it along this x-axis here somewhere. Let's plot it here, for example. And what we're going to do is find, in this case, the area to the left of that test statistic. And that is called the p-value, the probability value. It's the probability of getting this test statistic or something more extreme. What do we mean by more extreme? Further away from the mean of 0. So if we get a test statistic, we plot it, and anything more extreme than that in the left tail test would be in the left direction here. And how do we find this? If it's this area here, well, it's a probability. So we're going to use, if this is a standard normal curve, we're going to use normal CDF to find the area to the left of this number. So the lower endpoint is going to be -1,000. The upper endpoint will be the test statistic value. 0 would be the mean. 1 would be the standard deviation if this was a standard normal. If it was a T, we would use T-CDF. And again, the same idea, -1,000, lower limit, the test statistic would be the upper limit, and then the degrees of freedom would be what we enter based on sample size -1. And if it's a proportion problem, if this is P instead of mu here, it's the same thing. We use the Z. Normal CDF is what we would use. Now, if the alternative hypothesis has greater than, notice it's pointing to the right, we would use a right tail test. And we would plot our test statistic here, and we would find the area under the curve to the right. That is the area that represents all the values that are the test statistic or bigger. More extreme means bigger in this case because it's further away from 0 to the right. So the area to the right here would be the p-value. And finally, the third type of test is when the alternative hypothesis is not equal to. This is called a two-tail test. So, depending on the result of the test statistic will either be negative or positive. If the test statistic is negative, then we plot it over here, and we would find the area to the left, just like we did in the left tail test. But because we have to account for both of these tails in a two-tail test, it is not equal to. So it's either to the left or to the right. Half of the p-value is going to be the area that we found, and we have to therefore multiply that area or probability. If it's normal CDF, for example, we get a number, a probability. We need to multiply it by 2 because this p-value, this area here is not the p-value, it's 1/2 the p-value because the other half's over here. In the same way, if we calculate our test statistic and it ends up being positive, we would plot it here, find the area to the right as if it was a right tail test, and then whatever probability that we get, we multiply it by 2 to get the p-value. So for a two-tail test, we do the same thing that we did for the other two, the one-tail test, with the exception that whatever probability we end up with, we multiply it by 2. For the one-tail test, we don't do that. We simply, the area that we find is simply the p-value. All right, so these are called the 3 types of tests. And the problem, the wording of the word problem, will tell you which of these 3 tests that you do. And also, the alternative hypothesis will tell you it also. But if the problem doesn't give you the null or alternative, you have to actually figure that out first, determine what type of test that you're going to do, left tail, right tail, or two-tail, and then you actually do the work and find all the information that you need. Okay. So identifying the nature of a hypothesis test. All right. So we're going to do a couple of examples here. For number 1, a school publicizes that the proportion of its students who are involved in at least one extracurricular activity is 61%. Well, that says equal to is the null hypothesis. Equal to is one of those choices for the null. That means the complement, the alternative, must be not equal to. Since the alternative is not equal to, we're going to do a two-tail test. All right. And again, when we calculate the test statistic, it's either going to be negative or positive. If it's negative, we find this area and multiply it by 2. If the test statistic is positive, we find this area and then multiply it by 2. Let's look at number 2. A car dealership announces that the mean time for an oil change is less than 15 minutes. Less than is one of the choices for the alternative hypothesis. That means the null is greater than or equal to. But the alternative hypothesis is what determines the type of test. Since it's less than, it is a left tail test. And so whatever test statistic that we calculated, we're going to find the area to the left, and that will be the p-value. And finally, number 3 says a company advertises the mean life of its furnaces is more than 18 years. More than is one of the choices for the alternative hypothesis. Since it's greater than, we're going to do a right tail test. And this blue area here is going to be your p-value. But we calculate our test statistic, we'll plot it, and then the area to the right of it is going to be the p-value. We'll do actual examples of this next time, actual word problems. Now, here's one of the big keys of doing hypothesis tests. This box right here, this is probably another page that you may want to print out and keep next to you when you are doing your homework or taking a test. It's basically the decision rule based on a p-value. Now, there's an alternative way of doing hypothesis tests, but I will be strictly looking at the p-value straight through all 4 sections of this course. We're going to calculate the p-value and compare it to alpha. Your textbook will give you the alternative way, and I will show it to you when it shows it, but most students will prefer doing the p-value method. It's just simpler, and in real life, when researchers do this type of research, they always use a p-value. They never do that alternative way. So anyway, let's suppose that you calculate your test statistic, you determine whether it's a left tail, right tail, or two-tail test. You calculate your p-value. So now you have this p-value. It's a probability. It's between 0 and 1. And then you're going to compare it to the alpha, the probability of a type 1 error. And remember, the probability of a type 1 error is the maximum probability of making that type of error. So here's the deal. If the p-value represents a type 1 error also, and it's less than or equal to the alpha, well, that's considered to be what? Acceptable. Acceptable. A p-value indicates it's acceptable amount of type 1 error. And that means we are given permission to reject the null hypothesis, which is what the researchers wanted to do in the first place. So here's the rule. If the p-value, p, is less than or equal to alpha, we can reject the null hypothesis. If the p-value is greater than alpha, if the acceptable amount of type 1 error, the probability of a type 1 error, alpha, let's say it's 5%, and your p-value is 8%. Well, you said 5% is the maximum amount of type 1 error you would be able to accept, and now you're coming up with 8%. Well, that's not acceptable. So, given that fact, we're not going to end up rejecting the null hypothesis. In that case, we could say there's not enough evidence to reject the null hypothesis. So when the p-value is less than or equal to our alpha, the level of significance, the probability of the maximum probability of a type 1 error, all of that means alpha. If our p-value is less than or equal to it, we can reject the null. If it's greater than alpha, we will not reject the null. We'll fail to reject it. And that's the decision rule. Simple as that. And that's all we do. So it's very good to have this in front of you when you're going to be doing your homework and taking a test. Remember, you're going to be at home now, which is an advantage. So typically, you'll be doing it, we'd be taking tests in class, which means number one, you'd have test number 3 in class. Now, you would have a formula sheet, which you could have some of this information on. But for the final exam, you wouldn't have had that. But since we're not going to have a final exam this semester, and the test 3 is you're going to be doing at home, you can simply have these things in front of you, like this decision rule, so that you can reference it whenever you need it. Okay. All right, so that's it. All right. So again, what we're going to be doing is actually using this in the next 3 sections, using this decision rule. Okay. And there's some more things here that they go over. This could be a little confusing to you, that page there, so I'm going to skip it. Strategies for hypothesis testing, you can read through this. Gives you some pointers about how to read a word problem and pick out what you need. When we actually do this in the next 3 sessions, next time I'll be covering 7.2 on next Tuesday, 7.3, and a week from Thursday, 7.4. We'll be picking apart word problems, and I'll be showing you how to do all this. So it's here in section 7.1 if you want to review it now. I don't know if it will mean anything to you right now, but you may want to go back and reference it when you actually do 7.2, 7.3, and 7.4. Okay. So what I'd like to do now is to actually go through some exercises at the end of this chapter, and then we'll call it a day for 7.1. All right, so let's go through actually this first page here. Let's look at the true and false section here. And I think we should be able to answer these questions true or false based on what we have already learned today. So number 5, for example, says in a hypothesis test, you assume that the alternative hypothesis is true. Well, think of the criminal trial. I mean, do we really assume that the person is guilty up front? No, we assume that they're innocent, which is the null hypothesis. So we assume in a hypothesis test that the null hypothesis is true, not the alternative. So 5 is false. 6, a statistical hypothesis is a statement about a sample. No, it's a statement about a population parameter, not a sample statistic. So that's obviously false. 7, if you decide to reject the null hypothesis, then you can support the alternative hypothesis. Yes, of course. That's the whole idea of it. If there's not enough evidence to reject the null hypothesis, then there is sufficient evidence to support the alternative hypothesis. 8, the level of significance is the maximum probability you allow for rejecting the a null hypothesis when it's actually true. Remember, the level of significance is the probability of a type 1 error. So a type 1 error means rejecting the null when it's actually true. Well, yeah, that's what 8 is saying here, so that's true. Number 9, a large p-value in a test will favor rejection of null hypothesis. No. It's when the p-value is smaller, when it's less than or equal to alpha. So that's obviously false. And number 10, to support a claim, stated so that it becomes the null hypothesis. Well, the claim could be either the null or the alternative hypothesis. So that's false. All right. Let's look at stating hypotheses. That's the next one. All right. Now, I've actually printed out the answers to all of this, but I'm going through it quickly. I'll show you some of these if just telling you words is not enough. Let's go back. All right, in these exercises here, we're only going to look at 11 and 12 and 15 and 16, because we're not going to be doing hypothesis tests on standard deviations, which is 13, and variances, which is 14. So just ignore those two. Now, mu is less than or equal to 645. We have to determine whether that's the null or alternative. Well, since this has equal to in it, that must be the null hypothesis. So let's go back to the sheet here. So the null hypothesis is less than or equal to 645. That means the alternative has to be greater than, right? It's the complement of less than or equal to. So in this case, the claim is the null hypothesis. Number 12 says mu is less than 128. Well, less than is one of the symbols we can use for the alternative hypothesis. So alternative hypothesis, mu is less than 128 is the claim. So the claim in this case is the alternative hypothesis. Therefore, the null has to be the complement of it greater than or equal to 128. Go to 15. P is less than 0.45. Oh, that's also the alternative hypothesis, but now we're using P, the population proportion, as our test, as our hypothesized parameter. So P is less than 0.45 is the claim, which is the alternative. That means the null must be greater than or equal to 0.45. P is greater than or equal to 0.45. And finally, the last one says P is equal to 0.21. Well, that obviously equal to is the null. Its complement must be not equal to. That's the alternative. So in this case, the claim is the null hypothesis. All right. Now we're going to do identifying a test on the same page here. So let's go down. All right, we're going to look at number 20, 21, and 24, where you have to determine whether it's a left tail test, right tail test, or two tail test. Now remember, we ignore the null hypothesis. We only look at the alternative hypothesis when we determine what type of test. So this is a greater than symbol in the alternative. This is a right tail test. And number 24, not equal to, is the alternative. That's a two-tail test. By the way, if we could ignore these symbols here, if you look at this one here, number 22, it says less than in the alternative. This is left tail test. All right. All right. Let's go to the next page, 360. And we're going to look at stating the null and alternative hypotheses if everything's in words. Can we do that? Well, absolutely. The thing that we have to determine is what kind of parameter are we looking at? Are we looking at a mean, which means we're measuring something? Or are we looking at a proportion, which in essence, we're counting people or things and then finding the proportion of all those possible things, right, in the sample. Anyway. It says here a tablet manufacturer, number 25, a tablet manufacturer claims that the mean life of the battery for a certain model tablet is more than 8 hours. Well, number one, 8 hours is a measurement, which means it's a mean, and more than is greater than, which means it's the alternative hypothesis. So notice in this case here, let's scroll down. So the claim is that the mean is greater than 8 hours. That's and it's mu in this case here, since it's time, which is a continuous variable. We're going to use mu here. Mu is greater than 8. And that means the null hypothesis is less than or equal to. Let's look at number 28. An amusement park claims that the mean daily attendance at the park is at least 20,000. At least is greater than or equal to. Well, that has equal to in it, which means the null hypothesis. So greater than or equal to 20,000. Now this is 20,000 here, all right? We are counting people here, all right, but it's not a proportion. So we're going to use mu in this case here. So just be careful with that. We are going to use mu. So since it's at least, it's the null hypothesis, that's the claim. Mu is greater than or equal to 20,000. That means the alternative is the complement. Mu is less than 20,000. And finally, number 29. According to a recent survey, 73% of college students did not use student loans to pay for college. 73% of college students didn't. Now, it's stating 73%. It's not saying less than 73% or greater than 73%. It's saying 73%. So this means equal to, and therefore this would be the null hypothesis is P, it's a proportion, is equal to 0.73. That's our claim. The alternative must be the complement of it. P is not equal to 0.73. All right, now we're going to get to problem number 31. We're going to identify type 1 and type 2 errors. Okay. We'll spend a little time on this. And then I think that'll be it. I think that's all we'll be doing. All right, so we'll wrap things up right here. So let's look at number 31. And when we identify type 1 and type 2 errors, we have to state the null and alternative hypotheses first. All right. So number 31, repeat customers. A used textbook selling website claims that at least 60% of its new customers will return to buy their next textbook. At least means greater than or equal to. That's the null hypothesis. And it's 60%, that's a proportion. So we're going to say P is greater than or equal to 0.60. That's our claim. The alternative must be the complement of it, less than 0.60. Now that we've written down the null and alternative, let's talk about type 1 error. The type 1 error means we reject the null and we go with the alternative. And unfortunately, with the type 1 error, the null is true. So we have enough evidence to reject the null, go with the alternative, but in reality, the null hypothesis is true. So how do we state that in words? We would say we would reject the claim that at least 60% of its new customers will return to buy their next textbook when the claim is actually true. All right. So in other words, we're rejecting this claim. We're saying that the bookstore will have less than 60% of their returning customers or customers coming back again, when in actuality, at least 60% are coming back. Now, what is the type 2 error? Well, we're not going to reject the null when the null is actually false. So we're not going to reject this claim. So we're going to say not enough evidence to say that the bookstore is going to have less than 60%, when in reality, it will have less than 60% of the customers coming back to buy again. That's a type 1 and type 2 error. Let's look at 32. 32, it says flow rate. An urban planner claims that the noontime mean, hold on one second here. There we go. An urban planner claims that the noontime mean traffic flow rate on a busy downtown college campus street is 35 cars per minute. So 35 cars per minute are flowing through some intersection where they're counting the number of cars per minute. 35 cars per minute. Maybe when things are slower, it's far fewer than 35 cars per minute. All right. They use the word is 35 cars per minute, the mean traffic flow. So that means that mu is equal to 35 must be the null hypothesis. That's our claim. All right. Now, I said mu. Was I wrong? No. Here it is, mu, 35 cars per minute. Now, are we counting the number of cars? Yes, but it's not a proportion. We're not counting the number of cars, and we're not dividing it by the total number of cars that go through the intersection. So we're not taking the proportion of cars that go through. We're just counting the number of cars per minute. So this is considered to be mu equal 35, and therefore the alternative is mu is not equal to 35. So type 1 error would be, we're rejecting this claim. Claim is the null hypothesis that noontime traffic is 35 cars per minute when it actually is. In other words, we're saying it's something other than 35. We have enough evidence to say it's something less than or greater than 35, but it actually is 35. That's a type 1 error. The type 2 error would be not rejecting the null. That is that we do not have enough evidence that it's different from 35, when in reality it is different from 35. That's the type 2 error. Now to 34 or 33. Are we doing? No, we're skipping 33 because it's a standard deviation problem. Let's look at 34. A researcher claims that the percentage of adults in the United States who own a video game is not 26%. Well, is not means not equal to. That's the alternative hypothesis. It is a proportion problem, so we're going to use P. So P is not equal to 0.26 is going to be the alternative hypothesis. That's our claim. And the null hypothesis is that it is equal to 0.26. So what is the type 1 error? Well, the type 1 error in this case, since the claim is the alternative, we would say we're going to support the claim because when we reject the null, we're supporting the claim because the claim is the alternative. So that's the words we're going to use. We're going to support the claim that the percentage of adults in the US who own a video game system is not 26%, when it actually is 26%. That is, the null hypothesis is true. That's our type 1 error. Our type 2 error would be, do not support this claim. In other words, there's not enough evidence to reject the null and support the claim. So we're not going to support the claim that the percentage of adults who own a video game system is not 26%, when it actually is not 26%. All right, so it's a little bit of a more complicated type of thing here, but that's what it means. Number 35, let's go to 35. A campus security department publicizes that at most 25% of applicants become campus security officers. At most means less than or equal to. It has that equal to in it. So that means less. That means it's going to be a null hypothesis. 25% proportion. So we're going to say for the null hypothesis, P is less than or equal to 0.25. Here it is. That's our claim, which means the alternative has to be P is greater than 0.25. It's the complement of less than or equal to. Type 1 error, again, we reject the claim in this case, since it's the null, that at most 25% of the applicants became security officers, when in fact, that claim is true, that indeed it was less than 25%. So we're rejecting the claim that it's less than 25, or at most 25%, when it really is at most 25%. That's the type 1 error. Type 2 error would be not rejecting the null when the null is actually false. So we're not going to reject this claim when there are more than 25% of applicants becoming security officers. That's a type 2 error. And finally, the last one, number 36, a cell phone repair shop advertises that the mean cost of repairing a phone is less than $75. Is less than is the alternative hypothesis, because the less than symbol is one of the symbols for the alternative hypothesis. So in this case, it's going to be a mean, since we're measuring money, counting money. So it's going to be mu is less than 75 will be the alternative hypothesis. That's our claim. And the null hypothesis is the complement of it, greater than, mu is greater than or equal to 75. So type 1 error, again, would be rejecting the null, but in this case, supporting the claim. When we reject the null, we're supporting the claim. So we're going to support the claim. Then the mean cost of repairing a phone screen is less than $75 when it costs at least $75 in reality. That's the type 1 error. The type 2 error would be not rejecting the null when the alternative, when the claim is actually true. So type 2 error will be do not support the claim. In other words, we're not going to reject the null. We're not going to support the claim that the cost is less than 75 when it actually is less than 75. Okay, and it actually is less than 75. That's a type 2 error. So this is a little bit of a subtle thing here with type 1 and type 2 errors. It takes some getting used to. Will I be asking a lot of questions on your next test? There will be maybe 1 or 2 questions at most on type 1 and type 2 errors. So it's not a big thing, but if you can sort of master this, it's a fairly easy problem to get right on your test because there's no calculations involved. You simply set up your null and alternative hypothesis and then look at the type 1 error. Just remember a type 1 error, be rejecting the null when the null is true, and the type 2 errors are not rejecting the null when the null is false. That's all you need to know. Again, having that little chart with type 1 and type 2 errors will be useful to have in front of you when answering these types of questions. All right. So that is it for today. We just covered 7.1, basic introduction to hypothesis tests. We covered about what a null hypothesis is, what an alternative hypothesis is, how to write them, okay? We talked about alpha, the probability of a type 1 error, beta, the probability of a type 2 error. We said that alpha is used in the testing process, and it's called also the level of significance. We also talked about the p-value, what that is, how to calculate it, and we'll talk more about that, show you how to calculate it next time. Talked about the decision rule, how to compare the p-value to the alpha. When p-value is less than or equal to alpha, we reject the null hypothesis. When the p-value is greater than alpha, we do not reject the null hypothesis. And then we talked about the 3 types of tests, because we have to calculate what's called a test statistic before we do our p-value. And we have to know, of course, what type of test we're going to do. Is it a left tail test, a right tail test, or a 2-tail test? It is all determined by the alternative hypothesis. And the alternative hypothesis has a less than symbol. It means a left tail test. When it has a greater than symbol, it's a right tail test. And when it has a not equal to symbol, it is a 2-tail test. And then we do our p-values. And the important thing is that when we do a 2-tail test, when we do our calculation of the area to the left or to the right, we have to multiply it by 2 to get our p-value. All right, and we don't multiply by 2 when we do a left tail test or a right tail test. So that's sort of a summary of what we covered today. We're going to apply it more next time in section 7.2, which I believe we're going to be doing hypothesis tests for a population mean when we know that when we are given the population standard deviation. All right, so we're going to do that next time. And that's it for today. So have a very nice day. And I will probably later tonight post the homework for 7.1, and it will be due again on May the 8th, like all the other homework we've been doing lately. All right. So again, on Thursday, I'll be doing 7.2, a video for 7.2, and also we'll have our Q&As in the afternoon. Section 81, we'll have the Q&A at 2:30 p.m. on Thursday. Section 80 will have the Q&A at 3:30 on Thursday. All right, so that is it for now, and I will see you next time. Have a good evening.